questions? Yes?
I just want to see if you can go over, one of these questions from the flow test.
The number one there,
Yeah.
the harmonic tube. So third harmonic, 0.8 meters. Representation, wavelength. How many of them? Yeah, we can see what they are. So 0.8 meters. All right, it's the long hollow tube. So we have two open ends, or two free ends in terms of wave motion. A free end, node or antinode?
Antinode.
So whatever it is, I'm going to have an antinode at each end. That's the simplest, that's the first harmonic, and then I add a half wave each time. So that's the second harmonic, third harmonic. Badly drawn. That's pretty sad. Wow, still horribly drawn, but not as bad as it was before. So this is the third harmonic. Or if you picture the first harmonic, if you recognize that as a half of a wave, and that each harmonic we go after that, we're going to add a half wave. So the second harmonic, we add a half a wave. The third harmonic, we add a half a wave. And so ultimately, there's going to be 3 half wavelengths, or 3.5 wavelengths, or sorry, not 3.5, 1.5 wavelengths. So that would be answer to part B. Part A is the drawing, the representation of it. That's what I have up here. One thing I noticed is that students, especially if they're in a hurry as they're going through it, just please recognize this is an antinode here. Sometimes students, as they're doing it, get a little overzealous and will do something like this at the end, where the antinode really is there, but they keep going, and I'm never quite sure how to deal with that. So just stop it at the antinode. Right, questions up to here? There's still 2 more parts.
Okay. What would that look like with one fixed end?
One fixed in.
Yeah.
Well, that's the first harmonic with one fixed in. Then we add a half a wave for the third harmonic. With one fixed, one free, you have only odd harmonics. So that would be the third harmonic. So horribly bad drawn. That's better. So the third harmonic with one fixed and one free end is a fish.
I'm a Pisces, I get it.
All right. Other questions?
So the test is on Friday, and then how many questions is on the test?
I don't know yet. Look at the old test. That's probably the best
Okay.
way of indicating. I try not to do them too far in advance. I also don't like doing them at the last minute, so there's a sweet spot somewhere in there.
For the antinodes, you count the ends.
And yes, this is an antinode. So 1, 2, 3, 4 antinodes.
I know I asked this before, but is this test cumulative or is it just from?
15 onwards.
Okay, that's
Explicitly, I should say. I mean, if I talk about forces in it, I'm not testing you on forces. I'm assuming you already know what a force is. But you're not doing a force diagram like you did on the first test. So Riley and Ashland. So Riley, then Ashland.
So the nodes are the part they like cross? There's
Yes.
3 of them?
Yeah, the nodes are the points where it, in theory, is not vibrating. And Ashland?
So are the harmonics the halfway point between the antinodes?
The halfway, oh, here?
Between like the bubble, like the node?
You asked if that's the harmonic. When you're in a harmonic, so if this is a transverse wave, so we're outside with the slinky on the ground. If it's a transverse wave, it looks like this spot right here almost is in two places at once. You might have noticed in the vibrating string, it almost looked like the string was both of those places at the same time. So the harmonic is when you sort of get this pattern. So it's not really proper to say that that's the harmonic, but when you're at a harmonic, you should be seeing something like that.
So it's not all of.
You did not finish that question, did you?
No.
Okay. Did you?
I'll ask after.
Okay. All right, so the follow-up question was, what is the wavelength of it? So this was 0.8 meters on that particular test. Now, once I recognize that it's 1.5 wavelengths, or 3/2 of a wavelength, I just set that equal to the length. Because from here to here, I'm saying that's 3.5 wavelengths, I'm also saying that's 0.8 meters. And then solve for the wavelength. For the decimal fans out there, so I have 1.5 lambda is equal to 0.8, divide by 1.5. And again, lambda is equal to whatever that is. 8/15 meters. And the last part of that question was if the speed of sound is 340 meters per second, what is the frequency? And then this gets into the speed is equal to frequency times wavelength formula. And so we have 340 is equal to the frequency times 8/15, which is some decimal. And so frequency would be 340 divided by whatever 8/15 is. And then units?
Hertz.
Yeah. All right, Corinne, you started us off with this. Do you have any questions on this?
No.
Okay. Anyone else with questions?
Did hit record, didn't it? Yes. Okay.
Other questions?
Hold on, I do.
Yep.
That's the answer, or you're just gonna leave it at that?
I'm leaving it at that because I don't have a calculator with me.
Oh, okay,
Yeah, I do expect you to figure out what that is.
okay.
Only one fraction bar per number and
637.5.
237.5?
637.5.
There we go. Ashley?
How did you get 340?
It was given in the problem.
Oh.
The speed of sound roughly is 340 meters per second. There is a temperature dependence to it, but in that particular problem, I just gave it to you. In some of the old tests, I forget to give you the speed of sound. If I do that, just 340 is fine, or ask. Other questions? Okay. And that last other question was for things besides this. So don't feel like I was only asking about this one. Well, we last left off then. We talked about why opposites attract in terms of forces, the electric force, in terms of electric field, in terms of electric potential energy, in terms of electric potential. We had 4 explanations for the exact same thing. Then we talked about voltage, which is just electric potential difference. So if I have a 12-volt battery here, all I'm claiming, that's the positive and the negative side, is that this side is 12 volts higher than this side. I don't know what the actual potential is at this point or this point, but I know that the change in the electric potential is equal to 12 volts. And just because we don't want to make it too easy, those two V's are both capitalized, but they mean different things. That V is volt. This delta V here is voltage. Or just that plain old V is electric potential. So if I have an electric potential, where I know one side's higher than the other side, I know that negative charges like traveling to higher potentials, and positive charges like traveling to lower potentials. That was part of the opposites attracting and by repelling. So just negative charges. Like moving to higher potential. Positive charges, like moving to lower potential. So if we think about the atom, we have a nucleus here. And then we have these electrons floating around out here in some sort of cloud, and we call it a cloud because we can't see any more detail than that. So if anything is going to move, I've got a wire here with a whole bunch of atoms in it. If it's a copper wire, then I've got a bunch of copper atoms in it. Moving things in the nucleus is not particularly easy. And what's in the nucleus again?
Protons, neutrons.
All right. If I want to move a proton or a neutron, how would I do it? It's trapped. It's in the nucleus right there. There's more than one way of doing it.
Fission.
That's one way.
Fusion. Nah, that's adding.
Yeah, you probably can make the argument for it, especially with the easier way of doing it. The hard way would be to, fire a proton at a nucleus and split it for fission, or to cram two nucleuses together. And in a sense, that's the easy way too, except I'm going to move the protons in this desk right now and the neutrons. Here we go. There we go, did it. Since the atoms, what defines an atom is what's in the nucleus, we really can't move protons in and out of the nucleus. We have to move the whole thing. So when I'm talking about charges moving, for most of what your experiences will be, it's the electrons. And this should have been in one of the videos that you're supposed to have watched a week ago, whenever it's good. So I'll put down 99% of the time. It's the electrons that move. So if I have a battery there, with a positive side and a negative side. The positive side's got a whole bunch of positive ions in it. It's things missing electrons. And down here, I've got a whole bunch of electrons sort of sitting around waiting to go somewhere. Well, if this is the higher side, why don't the electrons just go straight up through the battery to the positive side? This is higher potential, this is lower potential. The electron's moving up, like moving to higher potential. Or, this is negatively charged, this is positively charged. The electrons are attracted to the positive, repelled by the negative. So we'll go that way. Or, I have an electric field traveling in this direction. The electrons like traveling in the opposite direction. Any way you want to look at it, the electrons want to move up to here, why don't they? Or how do I know they don't? What would happen if the electrons were allowed to just move to the positive end of a battery?
Would it change the voltage?
Indeed it would. What would it change it to?
It'd make it higher?
It's zero.
Why?
Because I have a bunch, the whole reason that there's a potential difference here is that I have a bunch of positive charges that want negative charges, and I got a bunch of negative charges that want positive charges. And if the electrons can move up here, they'll start neutralizing, and you're gonna lose that difference. All right. And you can drain a battery easily with external connections, but why don't they do it internally? What's preventing the electrons from just going up there and neutralizing the battery?
Is it something in the battery?
Yes.
I don't know what it would be, but is it something in it?
So the acid.
Okay, sorry?
The acid.
The acids is what is. Acids, I think this is acidic up here. I'd have to go back and look at that. It's not the acid that's keeping them from moving, it's the acid that wants to cause them to move. There is, and the technical word for it is barrier. There's a barrier in here. Now for the rechargeable batteries, the barrier is not as solid. And what it does is when you charge it, it basically forces electrons back. Now, as it does that, it weakens the barrier, and so that's why rechargeable batteries will eventually degrade and you can't really charge them up as much as you used to. But there's a barrier here to prevent that. Because we want the electrons to stay here, we want the protons to stay here until we're ready to make that change. We do that just by connecting. If I took a battery and I wrapped it in aluminum foil, battery would discharge, not instantly. It's a quick and dirty and potentially wasteful hand warmer. Because as the electrons move, it's going to keep running into things. If I have a wire here, it's filled with atoms, and I have an electron that, if I have an electron moving through it, it's going to hit and bounce and hit and bounce and hit and bounce, and every time it hits, it causes whatever it's hitting to move just a little bit, which, and the more it moves, we sense that as heat. So I have electrons basically, it's not a straight path in normal situations.
And they're losing energy, right?
Yes. And it's being transformed into kinetic energy, which we would sense as heat. So wires can heat up. Now, that particular electron is moving along, not particularly fast, but it is moving in a particular direction. So this would be the negative side and the positive side. Electrons moving towards the positive voltage, positive potential. This is known as the drift speed. And typical drift speeds would be in the order of centimeters per second, which is not particularly fast. But that will tell us, if I have a wire, I can sort of make some prediction about how long it takes for the electron to get from here to here. But I don't care really about that electron. All I need is some electron moving, because in order for that electron to move into here, as soon as I connect it, I'll have an electron here move in. leaving a hole. And then I'll have an electron here moving to that hole, an electron here moving to that hole, an electron here moving to that hole, and so forth. And so I'm gonna have a hole moving this way as I have an electron moving that way. And probably a bunch of electrons moving one way, a bunch of holes moving the other way. So electrons will flow from negative to positive. Unfortunately, we didn't know about electrons when we were coming up with conventions. Benjamin Franklin is the one I've seen credit to. Picture this whole thing that's flowing like a current. We use the water analogy, water flows downhill. If I have a potential here, a high potential and a low potential, he pictured current flowing from high to low. And so he set up this convention that was flowing this way. Now let that cover. What's flowing around like that is the current. We now know it's electrons flowing in the other direction, but by the time we figured that out, it was too late. We were stuck with it. So current, what we call an electrical current or current, flows opposite the direction of the electrons. I will sometimes see people who do solid state physics will refer to hole movement instead of electron movement. They'll label, we have electrons E minus, and the hole is H plus, and I've seen that occasionally. Not particularly fond of it, but just be aware that it exists. As you all know, we can't just keep writing current over and over again. Yes, Ashley?
So it's, the electrons go into the protons, not the, and the electrical current isn't the electrons, it's, trying to find it. So it's not like the protons and electrons going in opposite directions, it's the electrons going to the protons, the electrical current.
Yeah, going to those hungry protons that are in the top part of the battery.
So it's not the two going against, it's just the electrons going to.
Yes.
Okay.
That is correct.